about momentum. What is momentum and what can it tell us about two interacting objects? You can find more information on this in your notes and objectives for quiz 4C, momentum. The momentum of an object is its mass, or inertia, times its velocity. For momentum, we use the letter P, and the equation, when it's written out, the definition looks like this. Momentum is the mass times the velocity. Here we have a fast-moving car with a small mass and a slower-moving truck with a larger mass. And we can see that it's possible for a small mass moving quickly to have the same momentum as a large mass moving more slowly. So the slow-moving truck can have the same momentum as the quick-moving car. So how does the speed affect the momentum of an object? Here's a horse. So the horse changes speed from 5 meters per second to 10 meters per second. What happens to his momentum? And we see, since it's the same horse, the mass doesn't change. The velocity goes from 5 meters per second to 10 meters per second. In other words, the velocity doubles. In order to see how this affects momentum, we have to look at our equation for momentum. Momentum equals mass times velocity. And we're only interested in the velocity itself. So what is the effect of velocity on momentum? 4 typical choices are velocity, velocity squared, 1 over velocity, or 1 over velocity squared. And looking at our equation, just looking at velocity, we see it's just velocity, not velocity squared or 1 over velocity. So momentum is proportional to velocity. In this case, we double the velocity. Therefore, since we double the velocity, we double the momentum. So our answer, by changing its speed from 5 meters per second to 10 meters per second, the horse doubled its momentum. All right, what is the mass of a Pinewood Derby car if it has a momentum of 0.3 kilograms meters per second when traveling at 3 meters per second? So let's write out our givens. The momentum is 0.3 kilograms meters per second. The velocity is 3 meters per second. And the mass, we don't know. Our equation, momentum equals mv. So now let's substitute in our givens. For P, we have 0.3 kilograms meters per second equals m, we don't know, times v, times 3 meters per second. All right, so we want to get mass by itself. We have to get rid of the 3. So the opposite of multiply is divide by 3. Divide both sides by 3 meters per second. All right, and over here, this cancels. And these meters per second cancel those meters per second. Okay, so we got 0.3 divided by 3. You can use a calculator with that, or here's a little trick you can do to make this easier. Move the decimal point over that way, one spot. As long as you do it to both places, then the fraction will still have the same value. So I end up with 3 over 30 kilograms. Okay, well, the 3 on top cancels the 3 on the bottom, so I have 1/10, 0.10 kilograms equals the mass of the Pinewood Derby car. All right, so now that you know about momentum, what are some of the ways we can use this? One property you learn about is called conservation of momentum. Conservation of momentum means that when two objects interact, the sum of their momentums remains constant. Anytime something is conserved, it's constant. Constant, conserved, conserved, constant. That means it remains equal over time. So in this case, sigma sum means add up the momentums in the beginning initially, and then it will equal when you add up the momentums finally at the end. the best way to do this is just show you a couple examples. We're going to add up the momentums in the beginning before a collision or before an explosion, and they're going to be equal when we add them up after the explosion or after the collision. For our first example, we've got these two teams on skateboards, and they're going to push away from each other. Two teams are at rest on frictionless skateboards. The team on the left pushes away at 2 meters per second. How fast does the right team move away if the left team's mass is 1,000 kilograms and the right team's mass is 100 kilograms? Alright, first I'm going to write out my givens. I'm going to start my givens out with the team on the left. And I start out with the velocity, the left team initial. And that in the beginning, before they push away, their velocity, well, they're at rest. So it's 0. And then in the middle, I always put the masses. So the mass of the left team is 1,000 kilograms. And then the velocity of the left team final is after they push away. And it says they push away at 2 meters per second. And well, I'm looking at this picture. It looks like they're going to push that way. So that's usually our negative direction. So I'm going to make negative, nice big fat negative right there, negative 2 meters per second. All right, now we write the givens for the right team. The velocity of the right team initial in the beginning before it pushes away. Again, they're both sitting there at rest, so they're not moving, so that's 0. And then the mass of the right team. The right team's mass is 100 kilograms. And then the velocity of the right team final after they push away. Oh, that's what how fast we're looking for. Is the unknown. All right, well, next we're going to write our equation. So if you followed our pattern, everything on the left-hand side here, this is the mass times the velocity of the left initial, and the mass times the velocity of the right initial. That's going to be before the collision, and then everything on the right side over here, this will be the final. This will be the mass and the velocity of the object's final after the collision. So I can just bring these down, put them together, and write them out as an equation. So first, momentum of the left, mass of the left times velocity of the left initial, that's the momentum of the left team, plus momentum of the right team, so mass of the right times velocity of the right, that doesn't look good, velocity of the right initial. All right, it equals, now on the right hand side is the final. So mass of the left times velocity of the left final. That was these two right here. And now I write these two. Plus mass of the right times velocity of the right final. And next we put in our values. So I just go through and use these values in here. So I see this is going to be 0, so that's going to go away, and then this is going to be 0, so that's going to go away. Well, everything on the left is going to add up to 0. Now on the right side, mass to the left, that's 1,000, times velocity of the left final, which is -2, plus mass to the right, which is 100, times velocity of the right final. So this ends up being 0 equals -2,000 plus 100 velocity right final. Okay, so to get rid of -2,000, I have to add 2,000 to both sides. So plus 2,000 and plus 2,000. Okay, and these cancel. And now to get rid of multiply by 100, I have to divide both sides by 100. And this cancels here. So now I have the final velocity of the right by itself. And on this side, this 10 cancels that 10, that 10 cancels that 10, and I get 20 over 1. 20 meters per second equals the final velocity of the right team. And that's our answer. All right, let's try another one. An 80 kilogram goalie, initially at rest, stops a 5 kilogram hockey puck that was moving at 10 meters per second. All right, on frictionless ice. How fast do the goalie and puck move backwards during the stop? So here we have the puck, and it comes in like this, and the goalie's at rest, and then the goalie catches the puck like this, and then you can see they kind of both move back together. All right, so let's start with our givens. This time, I'm still going to end up with the goalie on top and the hockey puck on the bottom row. But I'm going to write a little bit different order than before, but it's going to be the same pattern. The mass is going in the middle, so I'll start right in the middle. Mass of the goalie equals 80 kilograms. Mass of the puck equals 5 kilograms. All right, and then on the left I got the initial velocity, so goalie initial velocity, velocity of the puck initial, and the right is going to be the final velocity, so velocity of the goalie final, velocity of the puck final. Let's put them all our values in now. So velocity goalie initial, he was at rest. The puck initial was moving at 10 meters per second to the right, so that's going to be positive 10 meters per second. The final velocity of the goalie, we don't know. And the final velocity of puck, we don't know. But this is a special collision because what's happening is, since the goalie is catching the hockey puck, this is going to be what we call a perfectly inelastic collision. Perfectly inelastic because they stick together. And since they stick together, we don't know what these velocities are yet, but we do know they're the same. So let's just call them velocity final, so that instead of looking like we're solving for two different things, we're actually solving for one thing, and they're both happen to be the same thing. All right, and now we write our equation, plug in our numbers, and solve. So writing out the equation. On the left-hand side, momentum initial, m times v initial. So mass of the goalie, velocity of the goalie initial, that was these two. And then we add mass of the puck, velocity of the puck initial, that was these two. Now on the right hand side, same thing for the final, mass of the goalie, velocity of the, well, I could put this, but it's the same as this, final velocity, so I'm just going to put final velocity right here. All right, and then mass of the puck times velocity of the puck final, but I'm going to do this again, velocity of the puck, velocity final, because it's the same for both. All right, and now we're going to plug in our numbers. On this side, velocity of goalie initial is 0, so this is 0, that goes away. Mass of the puck is 5. Velocity of puck initial is 10. Equals mass of the goalie is 80 times velocity final plus mass of the puck is 5 times velocity final. Okay, well, we can simplify this a little bit. There's different ways of doing this, but 5 times 10, that's going to be 50 on this side, equals, and I have 80 velocity final plus 5 velocity final, so 80 plus 5, that's 85 velocity final. And now I want to solve for velocity final, so I got to get rid of 85, divide both sides by 85, and this cancels, and we have 50 divided by 85. 50 divided by 85 in my calculator, it gives me 0.59 meters per per second. And that's the final velocity. And that's going to be the velocity of the hockey puck and of the goalie. Another word to look at that's useful when talking about momentum is impulse. Impulse is the force acting on an object times the time that the force acts on the object. It's often written like this: force times time. Don't let the little triangle confuse you. That just means amount of time in this case. It's always just, usually it's in seconds, and force is in newtons. So this impulse is often measured in newton seconds. Newtons times seconds. So you should be able to picture an impulse. For example, when a tennis ball is being hit by a tennis racket, the racket delivers an impulse to the tennis ball. You can just almost picture the force of the tennis racket and the time of impact on the tennis ball. Another example would be when two football players run into each other. You can just almost picture this force of this football player on the left just running into the football player on the right. The force and the time of impact. That makes an impulse. Force times time. So how does impulse relate to momentum? Well, it has to do with a change in momentum. A change in momentum is when an object changes its speed, its momentum changes. One way of writing that is like this: change in momentum. Remember triangle, that means delta. That's the Greek letter delta for difference, a subtraction. Subtracting the momentums. This is the final momentum, m times v final, minus the initial momentum, m times v initial. So again, you can picture the momentum changing in these examples above. So for example, the tennis ball was moving to the right, then it got hit and it started moving to the left. It changed its momentum from positive momentum to negative momentum. Down here, you can imagine here was this football player. He was running to the left like this. This guy was running to the left, and then he got hit by that football player and he got slowed down. So now he's going to be moving with less velocity to the left. But you can see that's a change in momentum. A change in velocity from fast to slow was caused by that impulse. So when we put these two things together, we get something known as the impulse momentum theorem. This left side is the impulse, force times the time, and this right side is the change in momentum. It should really be called the impulse change momentum theorem. One way that I like to think about it is like this. I like to think of the impulse as the cause. This is the thing that causes something to happen. Force times time. If you want to cause something to happen, you give it a force for a certain amount of time. The more force and the more time combined let you make something happen. On the right hand side, this will be the effect. What was the effect? The momentum was changed of the object. So in our first two examples back here, the racket put a force for a certain amount of time on the tennis ball and made the tennis ball change its direction. If the tennis racket hit for a harder force, it can make the tennis ball go back even faster. Here, the football player on the left put an impulse, force, and time on the football player on the right. And the more impulse, the more force and time he puts on that football player, the more he can change this football player's momentum. If he pushes hard enough, he could even push the other football player, backwards and change his momentum and push him backwards. So let's finish up by showing an example of how to use impulse momentum theorem. Here I have a 0.2 kilogram pinball. That's this pinball right here. Okay, and it's given a velocity of 4 meters per second. That's the velocity right there. It's shooting off at 4 meters per second. From this plunger right here. Here's the plunger. That's the plunger that gave it the momentum. So this is a two-part problem. First, it's asking A, what is the impulse delivered by the plunger? And then B, if the plunger took 0.3 seconds, that's a given, 0.3 seconds to launch the ball, what was the average force of the plunger? So this is a two-part problem. All right, first let's do A. What is the impulse delivered by the plunger? So this gets a little bit confusing, mainly because there's just so many options. Impulse is the force times the amount of time, but it's also equal to, you know, the change in momentum. The change in momentum is going to be mass times velocity final minus mass times velocity initial. So when a question asks for the impulse, you have to basically have two options. You can either try to find it using this part, which is the definition of impulse, force times time, or if you know the change momentum, you can find the change momentum and it's equal to that. So I'm looking at this problem and I don't see, I see time. That'll help us with this, but I don't see force anywhere up there. So I don't know how we could use this, because we don't know the force, to find the impulse. So what it looks like we're going to have to do is we're going to have to use this part to find the change in momentum, and that will give us the impulse. So that's going to be our strategy. Let's just find the change in momentum, and that'll give us the impulse. So I'm just looking at this as the mass times the final velocity minus initial velocity. So the mass, oh, right there, 0.2 kilograms. That's the mass. And now we just have to like subtract the two velocities. Well, the final velocity, it launched here at 4 meters per second. And its initial velocity, launched the ball. It looks like, I'm going to say, it looks like the ball was sitting at rest. When the plunger was pulled back, the ball was just sitting there. So it's going to be -0. That makes it kind of easy. So basically it's just 0.2 times 4. Well, that's going to be 0.8 kilograms meters per second. Okay, so the impulse is 0.8 kilograms meters per second, which is 0.8 Newton seconds, the impulse. Now the second part says, what was the force on the ball? What's the force on the ball? Well, looking at this, I now know the impulse. So the force times the time is the impulse, and it equals 0.8 Newton seconds. And I know the time, 0.3 seconds. So basically, force times the time, 0.3 seconds, equals 0.8 Newton seconds. And I want to get rid of 0.3 seconds. So basically, I just divide both sides by 0.3 seconds. And this cancels, and the seconds there cancels the seconds there. We get newtons, and I put that in my calculator, 0.8 divided by 0.3, and that gives me 2.7 newtons. You can see that this is not real tough, but it can get confusing because there's basically so many options that you might have to use. First, I found the impulse by knowing the change in momentum. That gave me the impulse. And then, once I knew the impulse, and I knew the time, I could solve for the average force. It took 2.7 newtons.